All right, welcome back to the session. The first talk will be by Meng Cheng, who's talking about ultra-common matter at finite temperature. Put out our profile.
Okay. Can everyone hear me? All right. I think the microphone is working. All right, first, let me thank organizers for inviting me and for putting together this very exciting workshop. As you can see on the screen, so I'm going to talk about UQM at finite T, which I feel strongly is a better title than the one I give on the schedule. The two interpretations both work. We are definitely having a meeting at finite temperature. And the subject is about a non-trivial state of matter at finite temperature, quantum state of matter at finite temperature. Okay, so this was the title I gave. So let me start by acknowledging my collaborators. So this work was done with a brilliant undergraduate, Shutong Zhou, who was at Nanjing University when he was visiting me and did all the work. But now I think he's at Chinese University of Hong Kong. Tyler Edison, who recently started a faculty member at Purdue University, and Kurt Van Kersenlink at King's College, Tibor Rakowski at Budapest School of Technology and Economics. All right, so a little about motivation. Some of you probably have seen this slide more than once. So we are very often thinking about phase of matter, topological or non-topological, in the context of a closed system, a pure state at zero temperature. That's where most of our beloved topological order states live. They're well isolated from environment. It's hard for them to survive under a very classical universe. Okay, but reality is obviously different. We have all kinds of imperfections, dissipation, decoherence, disorder, and temperature, of course. So there's an ongoing kind of program in understanding what happens for many-body phase of matter in the presence of all of these incoherent, in an incoherent environment. And there's a lot of interesting things to talk about, but among all the sort of incoherence that you can think about, the most familiar one is a thermal effect, that things ultimately they thermalize when you put a contact with a bath. Okay. So what do you do about this? Well, you can try to work very hard and do error correction, or you can just sit and give up, right? And the usual intuition is that once you heat things up, there's not much interesting going on. And let me just mention that this is, let me see if, actually works. Mention that this is closely related to the question of self-correcting quantum memory, although I'm not going to go deep into this in this talk. Okay, so now let me just list a few facts about thermal states. So a disclaimer that in this talk, and certainly on this slide, everything is about many-body states in the lattice model where you have finite dimensional Hilbert space per site. If you allow infinite dimensional Hilbert space, apparently the story is different. But first, let me say what I mean by trivial. So trivial or uninteresting state is the one which is a mixture in the sense of ensemble of short-range entangled states. Okay, so you can write the density matrix as a convex sum of short-range entangled states. I should probably put some probability weights in front of the state as well. Okay, so if you have a state that can be approximately written this way, then we say it's a trivial state. So here's a list of known facts. So a recent result last year is that above some constant temperature, every thermal state is trivial. In fact, it's not just trivial, it's fully separable. Okay. In one dimension, you can also show that thermal states are trivial for any temperature. That agrees with our intuition about one-dimensional systems. In two dimensions, Matt Hastings proved some years ago that if you have a commuting projectile Hamiltonian, thermal states are also trivial. Now, so far it's all trivial, and there's one more trivial that I've mentioned. That's so in 3D, you can also show that in the so-called CSS code, where many of the stabilizer models or exactly so models belong to, there's no finite temperature topological order. This includes the fractal models. So a special case of this was proven by Matt Hastings, and then later a more general argument was given in this paper. Now, if you go to 4 spatial dimensions, we know there is a non-trivial topological order state at finite temperature. That's a so-called loop-only toric code or two-form toric code. It's not so there are 2 kinds of toric code you can write down in 4 dimensions, and one of them actually remains a non-trivial quantum memory, a self-correcting quantum memory at finite temperature. Okay, so this is the landscape. This is some known facts, except in 4 dimensions, which is 1 above our physical universe. It looks very pessimistic, right? Everything's trivial, trivial, trivial. All right, but there's exactly 1 loophole in the arguments, and that's the main result I'd like to tell you about. That is, we find an example of a non-trivial quantum topological order in 3 dimensions, 3 spatial dimensions, that persists up to some temperature. Okay, and this is this state. This is the ground state not the ground state. This is a thermal state associated with a so-called fermionic toric code. Okay, so in short, the talk can be summarized in 1 sentence. The fermionic toric code exhibits long-range quantum entanglement at finite temperature and due to quantum anomalies. All right, so let me begin with the 3D bosonic toric code. Okay, and I might have to skip some of the slides. So this is a more familiar one. So let me actually write down the model. And as many of you are probably familiar with, toric codes are defined in a lattice system where you have 1 qubit per edge. So this is a cubic lattice with a qubit on each edge. Okay, and we have these Pauli operators, x and z, in the usual way. And we have this Hamiltonian where we have a term, a product of x, the red edges, on each vertex, and the blue edges, the product of z's around each plaquette. So these are the 2 kind of terms in Hamiltonian. And it's easily seen that this is exactly solvable. Every term commutes with every term. And so we can not only work out ground state, we can work out the entire spectrum, figure out thermodynamics and everything. Okay, let me first just describe the symmetries of the model. So you can either discuss in terms of excitations or in terms of symmetries, and I find it's a little more convenient to talk about symmetries for what I'm going to say. Okay, so there are 2 kinds of symmetries of the model. So here I'm taking symmetry to be a little more general than usual, although for this audience, I think it's probably not an issue. So this is really about higher form symmetries. And there are 2 kinds of higher form symmetries. One of them is a Z2 one-form symmetry, basically a product of X around some surface, closed surface. The other one is a Z2 two-form symmetry generated by a product of Z's along some closed curve. Okay, so both of them are non-anomalous, they're just products of X and Z's. But they anti-commute when you have one intersection between them. So they have a mixed anomaly, and that tells us that the ground state of this model is topological order, right? Okay, so we can also phrase it in terms of excitations if you open up these topological operators. So if you open up the membrane with the boundary, then you find a loop excitation along the boundary, which are the violations of plaquette terms. Or we can open up the loop, the blue loop, the product of Z's, and you find excitations on the vertices, right? So you can call these are the, and you can easily see that this is actually a bosonic particle. So you get a particle and it's bosonic. All right, so now let's look at the the thermal excitations. So we've already understood the two kinds of excitation in this model. You have these loop excitation, you have particle excitations, and both of them are excited at finite temperature. Okay? So at any finite temperature, you have a finite density of the particles. So you just have a finite density of them, they proliferate. Now, loop is a different kind of object, because if you want to create larger loop, you have to put in more energy. The energy is proportional to length of loop. So it turns out that there's a familiar energy entropy computation that sets a temperature, critical temperature scale, below which you have very little long loops, right? Loops remain short until some critical temperature, and then both point and loop excitations proliferate. Okay, so this is already kind of suggesting that there's something going on at low temperature, even for the bosonic toric code. So we can actually calculate thermodynamics. This was done by Castelnuovo and Chamon pretty early on. And you have a finite temperature phase diagram of this model. You can show that there is a transition between a low temperature phase where the loops are not proliferated and high temperature phase where everything is proliferated. And the transition is actually 3D icing. Okay. You can even calculate topological entanglement entropy using the usual sort of procedure. And you'll find, so I'm not going to give you the precise prescription of how to calculate this, but once you set everything up, you'll find that the topological entanglement entropy is whatever you expect from TQFT, topological quantum field theory, 0 temperature, and it immediately drops to some finite value, indicating the absence of loop proliferation up to that critical temperature, and then goes to 0. So nothing's interesting up to this, beyond this point. Okay. In terms of kind of information theoretical point of view, well, you have a quantum memory at 0 temperature, but it becomes a classical memory, and then above the transitions, no, the memory is completely gone. Okay, so this is a story for bosonic toric code, and even though there is a finite temperature transition, it was shown in this classic paper by Matt Hastings that this phase here is still short-range entangled. It's still trivial. From the thermodynamic limit of this is still a trivial state. Okay. All right, I was going to give a quick review of Hastings' argument, but feel like in light of time, I should probably run through this. Okay, I'm gonna skip all of this. It's a nice animation, but all right. Now let me talk about the actual model which exhibits a finite temperature quantum topological order. So this is a slight twist of the toric code model that we just discussed, which I call fermionic. It doesn't mean that system is actually fermionic. It has a fermionic excitation. The system is still spin. So everything I talk about is in spin systems. Okay, it looks very similar, right? This is the same Hilbert space with qubits on edges of lattice. Hamiltonian still has two kinds of terms. If you still remember what the terms look like from a previous slide, this terms remain the same. You still have a product of x around each vertex. Excuse me. However, around each plaquette, we do something slightly different. Okay? The blue one is still the plaquette operator, but now we multiply the plaquette operator with a bunch of x in a particular pattern. Okay? This is not random. It's chosen carefully so that they all commute with each other and does the right thing. Okay? So it looks complicated, but it's still exactly solvable, just product of z and x. And it's exactly solvable in the same way that the previous one is exactly solvable. Okay, so again, we can look at the symmetries, okay? Because this term remains the same, and the one-form symmetry is generated by basically multiplying these terms in some volume, and that leaves you some operator on the boundary. So the one-form symmetry is exactly the same as before, just some product of x operators. However, because the plaquette term is different, it modifies the two-form symmetry. So now this is a schematic drawing of a two-form symmetry generator. It's still a blue loop, means that you have product of z's along this loop. But because we attach these additional x operators to each plaquette term, you have to dress this blue loop with some x as you go around, right? So that X is like a little frame that rotates as you go along the loop. If the loop turns into different directions, you have to address it with different X. Hamiltonian, it might preserve some discrete subgroup of cubic symmetry. I'm not sure. Maybe it even has cubic symmetry, but it doesn't look. Okay, I'm not entirely sure. Some rotation symmetry is preserved, but not sure whether it's a false cubic. Okay. All right. Again, we can open up these operators and get excitations. Okay. So the membrane is the same. Open up the memory gives us the same kind of, exactly the same kind of loop excitations. However, if you open up the two-form string operator, we now get particles which are fermions. So that's a key difference between the two models. All right. So we can also look at the finite temperature phase diagram. Again, it's actually exactly the same, even the TC the same. So at low temperature, you have particle proliferation, but no loop proliferation. So there's a finite temperature transition, again, in the same universality class. Okay. All right. So, so the result can be, so let me summarize the result in a theorem. So we can make the statement a little more precise. That first, imagine you define this model on some finite torus of size L, and some temperature T, okay? We show that for any short-range entangled state, in the sense that it's defined on the first couple of slides, the thermal state of the fermionic toric code satisfies this relation, which means that it's very, very different from any short-range entangled state, okay, below some temperature T0. So here, F is a fidelity between two density matrices. No, I don't give I don't have a definition here, but it's a canonical measure of how similar two states are. If it's 1, means that two states are the same. If it's 0, means they are basically orthogonal. So the smaller it gets, means that the more kind of different the states are. Okay. Here, L infinity minus infinity means that this overlap, you just think of it as overlap, decays faster than any polynomial of the size L. Okay. So T0 is some constant temperature. And here I should say that I've set the energy unit to be 1 for all the terms in Hamiltonian. Okay. So the estimate that we give is T0 around 1.24, which is slightly below the thermal temperature 1.31. Surprisingly close. Okay. All right. So yes, I have 10 or 15 minutes maybe. Okay. So here I'm going to sketch a proof. This is a statement. This is a slightly more precise version and say that the state is non-trivial. We can quantify how far away this state is from the trivial state. Okay. And the reason that we want to do this is because regardless of whatever definition you want for non-trivial phase or topological order states, this fact probably puts it in the non-trivial category. All right, so let me now outline the proof. Okay. So we all know that thermal state is an ensemble where thermal state, you can diagonalize it in terms of eigenstate Hamiltonian with a bunch of excitations, loops, and particles. And the probability of such excitation is proportional to the Boltzmann factor, right, e to the minus beta energy. So the first step in the proof is that I'm going to apply what I call local decoder. It's just a finite depth quantum channel, a short depth quantum channel, to remove all the loops from the state. Okay? So you're going to get another state, which is not a thermal state anymore, and there's no loop in the state. There are still particles we cannot get rid of, but we can remove all the loops for when temperature is below T0. So this is called the loopless state. And then we're going to show that this state, even though it has lots of particle excitations, because the particles are fermions, the state has exact anomalous two-form symmetry, which then implies that this state is very different from a trivial state, but these states are related by a local decoder. In some sense, they are very similar. They are approximate They're not exactly the same, but no, they are similar. So the original state is also very different from a product state or a short-range entangled state. So that's a strategy. Okay. Yeah. In that case, it's exact non-anomalous. Yeah. So yeah, let me say a little more about this. So, oops. Right. So at this stage, you have exact anomalous two-form symmetry. I should put strong two-form symmetry here. The other one, the one-form symmetry, is even in this loopless kind of fixed point state is at most a weak symmetry. It's a weak symmetry. So you do have a strong weak anomaly, but that's not strong enough. That's not strong enough to put you in to guarantee long-range entanglement. Okay. So the local decoder that I just mentioned is actually a very concrete algorithm to clean up the loops in the thermal state. This was first described by this paper by Alex Kapita and John Priskill. I'm just going to very quickly sketch what the algorithm looks like. Okay, so this is a 2D projection of some loop configuration. Imagine you have some loops like this, the red lines, and you choose some direction lattice. Let's say it's a 1, 1, 1 direction. Okay, so we first identify the trailing vertices, the vertices below which all the loops kind of lie on one side of the vertices. These are trailing vertices. Okay, and then we just kind of push along the trailing vertex. You push the loop in that direction. So if you do this in the example, you'll see that the loops are pushed in that direction. Okay, this one is gone. Because we annihilate the loop with, we push in that direction, you get annihilated. Okay, and this one is also gone. So we keep doing this. We can show that all the loops will be annihilated after finite number of steps. And the number of steps scales nicely with the length of loop. In fact, a length L loop can be cleaned completely in 3L steps. Okay. All right. So now this is the fact, again, from just the consideration of energy and entropy computation, that we know the typical length of loop is only logarithmic in the system size at low temperature, below the TC. Okay? Therefore, we can apply the sweep decoder, the decoder I just told you, in this number of steps, and that cleans up all the loops. It basically cleans up all the loops. So the states with loops are exponentially suppressed below this T0 because of the computation between energy and entropy. And once we apply the sweep decoder with the number of steps logarithmic in system size, you get to a loopless state. Okay? So in short, you start from a thermal state at low temperature, apply the sweep decoder, you get to this kind of fixed point state with no loop, but still with all the particles. Turns out that you can actually do the other direction as well from a recent work. So these two states are really in the same class, okay, in some definition of the phase. All right, we don't need the second fact. All we need is the first one, that you can clean up all the loops. You don't have to be able to regrow all the loops out of the loopless state. Okay, the rest. So this is the first step of the proof. The second step uses the anomaly in the two-form symmetry. Okay, so as I said, the two-form symmetry anomalous. Haven't actually explained what that means, but it's basically another way of saying that the particles you get by truncating the loops are fermions. When it's a boson, it's not anomalous. All right, so in 3D, another convenient fact is that in 3D, we won't have fermions and bosons, and they all braid trivially with each other. Right? They have non-trivial exchange statistics, but if you take one around another, you get one. So that means even though you have lots of fermions around, the loop operator is still exact symmetry of exact strong symmetry of the state. Okay, so it's not affected by the presence of lots of finite density of fermions. Okay. So now we can give a very short argument. This is not quite sufficient. I mean, you can make it more precise basically and get to the theorem that I give you. but let me give a short argument first. So suppose you can write this looplet state as a convex sum of short-range entangled state. Okay? By some very elementary argument, you can show that each of them basically has to have this exact anomalous two-form symmetry. Once this convex sum has this two-form symmetry, strong symmetry, then each of them has to have. But that's not possible by the word anomaly. Right? The anomalous symmetries does not allow a short-range entangled state invariant under that symmetry. Okay? So that's a contradiction. You cannot, this is not equal to a short-range entangled state. Basically because a short-range entangled state cannot have emergent fermions if the system is made of spins. All right, so that's basically the extent of the argument. We can make it more quantitative by basically invoking a slight generalization of the argument in this paper, where we can bound the distance between the looplet state with any short-range entangled state and get this L to minus infinity. Okay, so there's also an error that you can bound in the previous step of cleaning the loop excitations. Both are L minus infinity. Together you get an error bounded by super polynomial function in the system size. Okay. All right. So I think I'm almost done. So just to kind of recap, so we have this statement that any short-range entangled state is very far from the state from the thermal state of Fermionic toric code below this temperature T0. And the proof is done in two steps. First, we clean up the loops. And then we show that this fixed point state we get after cleaning up loops is actually has this exact anomalous two-form symmetry. So it's very distinct, very different from a short-range entangled state. All right. Okay. So in fact, we have this kind of finite temperature phase diagram. It's not a thermodynamic. It's also the first thermodynamic phase diagram, but we can also understand what the phases are from a kind of a circuit perspective, right? So at 0 temperature, there's a distinct quantum topological Fermionic toric code phase. Once you go to finite temperature, the quantum memory aspect of this state is gone. You just have classical memory. But it's still non-trivial, as we just argued. Okay? So we can call this a fermion, kind of proliferated or fermion decoherent Fermionic toric code. Okay? Remains long-range entangled even though the quantum memory is lost. And then above TC is trivial memory. So we were able to prove this up to some T0, slightly below TC, although we believe that this is the correct phase diagram. Okay. All right, so there's some generalization to other symmetries, but let's, yeah. Yeah, so this is a bit like if you just run the naive counting argument, you'll find slightly lower temperature than the critical temperature Ising model. But so our argument, we didn't try to optimize that. We just do something that's enough to get us a temperature. It turns out to be, should be below TC, but we believe that you can go all the way to TC. Okay, let me skip this. Okay, so let me now just end with a bit of open questions. So the most pressing question here is that the argument really only works for this exactly solvable model with the commuting terms and everything. It will be very nice to understand the stability of the result up to perturbations. I mean, intuitively, you would expect that the long-range entanglement should persist if you perturb the Hamiltonian a little bit. Okay? But surprisingly difficult to actually show this. There's some very promising recent progress that kind of goes in that direction. For example, you can actually show the long-range entanglement is stable, assuming a certain clustering property of the correlations in the system in this recent work. Okay. Other questions that one can ask includes, for example, whether this is relevant to any experimental systems, such as a 3D Kitaev model, or how to actually get more informative diagnosis of long-range entanglement. Okay. So I think that's all, and thanks for your attention.
Can you some intuition for the this Fermionic model? What makes it? What allows this?
What allows this to?
Yeah. I mean, you mentioned fermions on the strings.
Right. Well, I guess the intuition maybe I can give is a bit like, in the bosonic, let's start from bosonic toric code where you have E and M excitations. E is just a bosonic particle. M is like the Z2 fluxes, right? So what happens in the fermionic toric code is a bit like flux attachment. It's not exactly because now the fermions, the particles and bosons are not even, they don't even have the same dimension, but in some sense, you can actually understand in terms of flux attachment that we bound some higher form symmetry flux to the fermion, to the particle to make it fermion. So maybe another example I can give that there's a parent phase of this Z2 fermionic toric code. That's a U1 gauge theory in 3+1D, where you have, in the usual way of writing this, you have electric particle bosonic and monopole also bosonic, and you can bind them to get a fermion. Now you Higgs this U1 to get this, and that this fermionic dion becomes this fermion. Yeah.
So is there any kind of measurement you can do to diagnose this phase?
Right. So this was not on the slide and was not even in the paper, but if you look at, so if you can measure, for example, these operators I discussed earlier, the membrane operator and the string operators, they have different scaling in these phases. So that doesn't directly prove the long-range entanglement, but that does allow you to distinguish them.
Yeah, so this coincidence of this entanglement phase transition and the thermodynamic phase transition seems to make sense.
Yeah, it seems to make sense. Yes.
This is a puzzle in my head. Is this cleaning up operation specific to unoriented loops, or the loops can be oriented?
Well, so I don't think it's, I think it's not that important whether loops are oriented or not. So the sweet decoder, you might worry that it cares about orientation of the loops, but there's an alternative construction that we give in the paper where we don't actually need to use a sweet decoder. It's convenient to give some bounds, but there's an alternative construction where we don't use it at all.
Then one could ask, if you took a U1 gauge theory where the monopole, let's say, is found, the charge of the you take the monopole to infinity. So there's a one-form symmetry which has itself a norm.
Right.
And there is a continuous closed loops in finite temperature. Would that be a whole?
I guess excitation are not just in terms of loops, right? Excitation are all particles in the U1 gauge theory. So you have photons, gapless photon, you have massive particles, but this doesn't apply to particles as far as I understand. Like once particles proliferate, we have nothing, you can do nothing about them. Oh, so you want set that to infinity. Okay, maybe this sounds like this loopless state. I haven't thought carefully about this, but if you strictly set it to infinity, maybe that has similar. Right. Yes. Sorry, maybe we can talk more about this. Hey, Max.
So like, is the intuitive picture of this that, at finite temperature have very few loops, and then you can kind of grab, like what's the thought experiment to diagnose this? Is it kind of you grab two of these fermionic charges and you braid them, and because most of the time you don't encounter a loop in the process, then you find that kind of.
Yeah, I mean, there's right, indeed. But most of the time you don't encounter a loop. You can exchange them, get a phase, and that's sharply different from any short-range entangled state. I think the proof, if you look carefully, the proof essentially does just that. Now, first you have to clean up loops, right? It just means that the loops give you very small correction to this. And then the way to give this bound is basically doing this and show that you cannot get the -1 out of a short-range entangled state. It's just writing it down more carefully.
So is the recognition
So you're saying there is this gas, obviously, in the fermionic charges.
Right. Right.
But the point is that because they're fermions, you know, when you twist the loop, it's really a full rating statistic, like this gas are fermions, you don't get extra minus ones.
You don't get extra -1 from full braiding, right? Yeah, so to see the anomaly, you need to do exchange. But to show that this anomalous two-form symmetry persists, that you need to check braiding, full braid. Right? The full braiding tells you that the anomalous two-form symmetry is still there. And the -1 tells you that this is actually non-trivial.
But you're saying the gas with fermion does not, because I've got a loop operator from the acting on one side of the density matrix, it gives you that kind of.
So does that mean that this loop operator is still a symmetry, a strong symmetry of the density matrix, right? If you have any loop, it spoils the symmetry because when you go around this loop, you pick up a minus sign. But they go around a particle, you don't pick up any minus sign. Actually.
If you have local fermions, let's say this is like a Heisenberg limit of a Hubbard model.
Yeah. Yeah.
Then there's no distinction between the bosonic.
Right, right.
So then you say both are finite temperature and time?
I was hoping this question doesn't arise. Yeah, so what I said only applies to spin system. We believe, although I haven't, we don't have an explicit proof yet, that if you have physical fermions, that will make this trivial. Basically, it's not distinct from just a trivial state of fermions. Once you can blend in some physical fermions, it's not, no, you just have finite density of fermions, that's all.
We have addressed all the questions. Let's thank them again.